special right triangles. There are two special right triangles. There's the 45, 45, 90 and the 30, 60, 90. So let's start with the 45, 45, 90. Where does that come from? If we take a square, we know that all the sides are equal and we know that the angles are 90 degrees. And if we draw a diagonal from one vertex to another, we will have just drawn a right triangle. Now that right triangle, because of the square and because of the fact that all the sides are congruent, that diagonal we have drawn also bisects those two angles. So we have just created a 45, 45, 90. Now, when we have drawn this, there's a special relationship between the sides of a 45, 45, 90 that always holds true. If we know that one side of the square is x, so should this side. So this 45, 45, 90 is therefore an isosceles triangle. And to find what the length of the hypotenuse should be, we can simply perform the Pythagorean theorem. If I have two sides of a right triangle, I can find the third using Pythagorean theorem. So we're going to take one leg squared plus the other leg squared equals the hypotenuse squared, which we don't know. Let's call that c. X squared plus x squared is 2x squared. If we're solving for the hypotenuse, we would take the square root of both sides. We can split this square root, so it's square root of 2 and square root of x squared. The square root of x squared is just x, so we can say that the hypotenuse should be x times the square root of 2. And that is the relationship that it should hold for any leg length of a 45, 45, 90. So what we will be using is what we'll call a reference triangle that will allow us to solve problems that are utilizing the 45, 45, 90 by understanding this side relationship that is formed. So how did we get this side relationship? We know that it comes from a square, and we just did, or we can just say, because both angles are 45 degrees, we definitely know for sure that those two sides are equivalent in length. So if we have any length x, this one will be x root 2. So this is your reference triangle for a 45, 45, 90. Now let's jump over to the 30, 60, 90. The 30, 60, 90, we can think of an equilateral triangle. Where if we insert an altitude, we will have bisected this opposite side and also bisected that angle. So if all the angles in an equilateral are 60 degrees, then this angle gets bisected into two 30s. Now we have a 30, 60, 90. And if all the sides are x, well, if we bisected this bottom side, well, this must be x divided by 2. Now, how do I get the length of the altitude? Well, I can perform the Pythagorean theorem. So I'm going to take x over 2 squared, and we're looking for the length of the altitude, so let's call that b squared, and we have x squared for the hypotenuse. So make sure you just set this up correctly. We'll square x squared, so we'll get x squared over 4 plus b squared equals x squared. If we subtract x squared over 4 from both sides, we'll have b squared equals x squared minus x squared over 4. I'll be able to combine these like terms. If I reformat it in the following way, maybe you'll be able to see it better. So I have two x squareds that I can combine. I have one x squared and I take away a fourth. So we're going to have 3/4 x squared as a result. Take the square root of both sides to solve for that missing leg. You can split this to simplify. We know that the square root of x squared is just x, and we can even split that ratio into the following. And we know the square root of 4 is 2. So we have successfully found a simplified version for our altitude length. So let's draw our 30, 60, 90, maybe a little bit better than that. The hypotenuse, if we call that x, then the side opposite 30 will be x over 2 because of the division or the bisection of that bottom side of the equilateral triangle. And through Pythagorean theorem, we found that the side opposite 60 will be root 3 over 2x. Now, we don't want to deal with these fractions. So to get rid of these fractions, all we have to do is scale this triangle by a factor of 2. So if we multiply all the sides by 2, we'll still have a 30, 60, 90 because we've magnified all the lengths by the same amount. And that will also get rid of the fractions. So our reference triangle, as we see most often, will be a scaled version of this. Now, the version we currently have unscaled, you'll see later in the course, will give you a more intuitive understanding, or not intuitive, but a better understanding of some of the trig stuff that we look at. But we don't want to work with fractions, so we scale everything by 2. This becomes x, this is 2x, and this becomes root 3, or x root 3, or root 3x. So this is the reference triangle that you'll be using in this class for a 30, 60, 90. So that's where they both come from. That's where the side relationships come from. Now let's look at some examples on how to use this stuff. So let's first look at some examples for the 45, 45, 90. I've already have the reference triangle drawn for us, which we're going to use, but there would be two scenarios that you would face. You would either be given a leg or you'd be given the hypotenuse and be asked to find the other sides. Now, if we were given 2 of the sides, to find the third, we could always use Pythagorean theorem. So when we come across a right triangle where only one of the sides is given, and we notice that it fits one of these special right triangles, whether we notice the acute angles are 45 degrees or 30 and 60, then that's a good hint that we're gonna be a special right triangle problem. So I only have one side of a special right triangle, and I need to find the other 2 sides. So again, if we had 2 of the 3 sides, we could just use Pythagorean theorem. Now, the luxury of the 45, 45, 90 is that it is an isosceles triangle. So if you have struggled with the idea of utilizing the special right triangles, you may notice that this is isosceles, and if I do have a leg, I could just say this other leg is 6 root 2 and use Pythagorean theorem to find the third side. So let's say for this problem, we just want to find the hypotenuse. That's the only thing it's asking. And for this over here, we just want to find one of the legs. When we are given a leg, again, you could just say the other leg must be 6 root 2 and use Pythagorean theorem. But if we want to use the reference triangle to get a good handle on how to use special right triangles, what you're going to do is the following. You are going to say that this leg that is given associates with this side here. So if x on my reference triangle is 6 root 2, then the hypotenuse, which is what we're looking for, must be that x value times the square root of 2. So this should be 6 root 2 times root 2, because the special right triangle of a 45, 45, 90 tells me that the hypotenuse should be what this is interpreted as, is the length of a leg times the square root of 2. That's how you should interpret that expression. So if I take the length of the leg and I multiply it by the square root of 2, that will give me the hypotenuse. So square root of 2 times square root of 2 is square root of 4. And the square root of 4 is 2, so 6 times 2 is 12. So that's how you can use a reference triangle, a special right triangle, to find a hypotenuse. And in fact, that is a much cleaner, easier, more efficient method than going through the Pythagorean theorem. So that's what you can do when you have a leg. Now, what if we have a hypotenuse? So let's erase some of this stuff. Well, it's going to be the same approach. You say, all right, the hypotenuse is 11. So on my reference triangle, I know that this thing should equal 11. Now, what I've done here is create an equation by saying x root 2 equals 11. And why that's significant is because that will allow me to solve for x. And the reason I would want to know that is because on my reference triangle, if I'm able to find x from what that equation I have boxed off in green, I'll be able to determine the length of the legs. So off to the side, let's say x root 2 we know equals 11. So dividing by the square root of 2, we can see that x on my reference triangle should be 11 root 2. So that would be the length of the legs. Now, we're not going to leave our answer like this. We don't want the square root in the denominator, so we're going to rationalize to get a simplified answer. We're going to get 11 root 2 over square root of 4, and the square root of 4 is 2. And there's your answer. So fully rationalized representation of the leg of a right triangle. That's a 45, 45, 90. Now, how did we know this was a 45, 45, 90? They didn't explicitly write 45, but those indicate that those angles are congruent, and we know that acute angles in a right triangle are complementary. So if they're both the same, they must both be 45 degrees. So I knew I was dealing with a special right triangle in that case. Now let's jump over to a 30, 60, 90. So here we have the 30, 60, 90. I have the reference triangle drawn for us, and we have three different scenarios. We'll either be given the side opposite, the 30 degrees, opposite the 60 degrees, or the hypotenuse itself. So in each question, we'll probably have to find the other two sides. Again, we have a right triangle, and we're only given one side. So to find the other two, in this case, we don't have the luxury of utilizing the fact that it's isosceles or there's some special relationship that we can just jump to Pythagorean theorem on. The special relationship that we're going to use is this reference triangle that we have off to the side. So if I have the side opposite 30, we know on my reference triangle that the side opposite 30 is x. So on my reference triangle, I'm going to say x is equal to 7 root 3 because that's given to me in the problem. So if x is 7 root 3, then on my reference triangle, I know the hypotenuse is supposed to be 2 times the side opposite 30. That's what that's saying. So the hypotenuse is 2 times the side length opposite 30. That is what the reference triangle is telling me. So if I multiply that by 2, by substituting in the side length opposite 30, we'll get 14 root 3. So 14 root 3 is my hypotenuse on this problem. The side opposite 60 is supposed to be the side opposite 30, or the shorter leg, times the square root of 3. So it's going to be 7 root 3 times the square root of 3. Square root of 3 times square root of 3 is square root of 9. Square root of 9 is 3, so 7 times 3 is 21. And there you go. We found all three sides. So if you found the first side and used Pythagorean theorem to find the third after that, so be it. Not an incorrect method, but more time consuming. So we found those two missing pieces. So let's jump over. What if you're given the side opposite 60 degrees? So if we're given the side opposite 60, we're going to go over to our reference triangle. We're going to say the side opposite 60 was given, and it is 15. There's an equation set up here, so it's not explicitly obvious what x is, and I want x so that I can find the other two sides using my reference triangle. So we're going to have to solve that equation by dividing by the square root of 3. We're going to want to rationalize this because we don't want the square root in the bottom. So we're going to have 15 over root 3 times root 3 over root 3, which is going to be 15 root 3 over the square root of 9, which is 3. And I can simplify this further because 15 over 3 is 5. So 5 root 3 is the value of x. So if x is 5 root 3, there's that side. And I know the hypotenuse should be 2 times x, so it's going to be 2 times 5 root 3, which is 10 root 3. So we have the missing side. So the side opposite 30 is 5 root 3, and the side that is the hypotenuse is 10 root 3. And just to double check, you want to make sure, again, your hypotenuse is 2 times the length of that shorter leg. And then the last example is, what if you're given the hypotenuse? If we're given the hypotenuse, which we know is 18, going over to my reference triangle, I'm going to say that this is supposed to be 18. So if that's 18, again, I have an equation here that I can solve, and many of you can probably just do this in your head, but we now know that x should be equal to 9 based on that equation. And if x is equal to 9, that will allow me to find the other two sides. So I know the shorter leg is 9, and the longer leg, opposite 60, should be 9 times the square root of 3, which is the most simplified version of that. So given the hypotenuse, we can find x. And from x on our reference triangle, we can find the other two sides. So side opposite 30 is 9, and then 9 root 3. So that's how you can use the reference triangles for 45, 45, 90s and 30, 60, 90s to find missing side lengths of special right triangles.